For our first panel, it's a Starship world. Please welcome to the stage Jonny Dyer, Christine Fox, and Ed Liu.
Hi everyone, can you all hear me okay? All right, great. Well, I'm Jonny. I am both an operating partner at Space Capital, and I'm also the founder and CEO of Muon Space, which is a portco. So a lot of ties in with a bunch of folks here today. And we're really excited for this conversation today. I've got a couple of folks with me on the panel, which I've known for several years to many years, and they're some of my favorite people in the world, so I'm super excited to have this conversation with them. And so I'm going to go ahead and introduce them first, and then we have a little bit of an intro, a few slides that just kind of motivate what Starship is. I think probably most of you in the audience have a sense for Starship, but it's good to kind of get a refresher on just kind of how big of a revolution it could represent. And then we'll just get into a conversation and cover a lot of different topics in terms of thinking through what it does represent and what it could mean for the future. So I'm going to start with Christine. So Christine and I have known each other for several years. We got to know each other a few years back on a National Academies study that we were both invited to participate in. Christine served in the Office of the Secretary of Defense from 2009 to 2014. During her time in the DoD, she served as the Director of Cost Assessment and Program Evaluation, or CAPE, from 2009 to 2013, and as Acting Deputy Secretary of Defense from 2013 to 2014. As Director of CAPE, she led several department-wide reviews related to operations, technology, and especially the budget. Upon leaving the DoD, she joined Hopkins Applied Physics Lab as Assistant Director of Policy and Analysis. In 2022, she transitioned to the position of APL Senior Fellow and began to serve in a variety of positions, including Board Director for Muon Space. So we are very lucky to have Christine as our independent director. She's also a consultant to Palantir Technologies, a member of the President's National Infrastructure Advisory Committee, or NIAC, and member of the Secretary of the Navy's S&T Board. Prior to serving in DoD, Ms. Fox served as president of the Center for Naval Analyses from 2005 to 2009 after working there as a research analyst and manager since 1981. So join me in welcoming Christine.
Thank you. It's great to be here.
And then Ed and I have known each other for a little bit, I think probably close to a decade now.
Yeah, 10 years.
Yep. Ed Liu has a very interesting and varied background. He's a physicist engineer. He's also a former NASA astronaut, and he's also co-founder of another Space Capital portco of Leo Labs. He's a CTO there. And he also is co-founder of a nonprofit called the B612 Foundation, which is focused on planetary defense. He spent the last decade working on solving large technical problems at the intersection of space, public policy, and computer science, including preventing things like asteroid impacts with Earth and preserving the Earth orbit environment from space debris in his work at Leo Labs. Prior to this, he was the leader of advanced projects at Google. His NASA career spanned 12 years, including flights aboard the space shuttle on STS-84 and 106, Soyuz TMA-2, and the International Space Station for Expedition 7. He's published peer-reviewed papers on astrodynamics, planetary science, high-energy astrophysics, plasma physics, solar physics, cosmology, and statistical physics. He's also published technical policy-related editorials in the New York Times, Wall Street Journal, Financial Times, and Scientific American. So please join me in welcoming Ed as well. Great. All right, so I'm going to jump into a few slides just quickly to motivate the panel a little bit. We're going to talk about what is Starship. So, Starship it's kind of hard to fathom the scale of it. It is the largest rocket ever built. Its goal is to put roughly 150 tons in orbit every time it launches. For scale, I have kind of a graphic on the right that shows how it compares with some of the other large rockets of history. Obviously, the previous record holder being the Saturn V that got us to the moon in the 60s. And so, it really is kind of, again, very hard to fully grok just how big of a piece of equipment Starship is and how capable it will be. It's also the first fully reusable rocket, so it's designed for both stages to come back to the launch site. As y'all know, Falcon 9 today, SpaceX's kind of workhorse, his first stage is reusable, but the second stage is not. So this is now the first time that there would be a fully reusable capability. And it's really designed for regular airline-like operations. That's at least the stated purpose. It enables some other interesting things. So it's also designed for in-orbit refueling, and I think we'll talk about that a little bit and what that enables. And then, just given the size and capability, it really allows us to start thinking in a much bigger way about things beyond low Earth orbit, which is the primary purpose that Starship is created for. Yeah, so I think we want to kind of think about two primary areas of impact for what Starship will do to the space ecosystem. So one is just, again, in low Earth orbit. It's going to provide the ability to put much more things in orbit than has ever been possible before. So there's clearly going to be impacts from that. And then I think secondly, when you have this ability to put so much mass in orbit and do things like refueling, it really opens the door to doing things beyond LEO. So we'll talk about that a little bit as well. So one of the other things I wanted to do to just motivate this conversation a little bit, and this graph is inspired by one that Ed made, I think last year, which is basically just to give some background on what's going on in LEO right now. So this is a plot of the number of satellites operating in LEO as a function of time, going back to the kind of the early 2010s, which is sort of the start of what we consider kind of the new space era. And I think the really dramatic thing is that if you look at the slope of this line, this is on a log Y scale, starting in about 2020, we're going to a doubling rate of the number of things in orbit about every 18 months. This is the same as Moore's law, a similar scaling trend to Moore's law that happened in semiconductors starting in the 70s. And so we're already in this kind of exponential growth sort of phase of space development. And obviously now that we think about something like Starship coming online, it could accelerate this even further. The other thing I think that's important to think about with this is not just the numbers, but also the cost and the unit economics of this. So this is a little bit of an eye chart, but the real rough takeaways here are that if you look at what it costs to put a kilogram of mass in orbit today with Falcon 9, it's something like $2,000 a kilogram. If you extrapolate to what's possible, kind of theoretically possible with something like a Starship launching very, very, very regularly and sort of economically operating at sort of similar levels to what like airlines operated today, you could imagine at least another order of magnitude reduction in cost of mass to orbit. And so again, there's already been order of magnitude that's come down in the last 20 years or so. You imagine another order of magnitude and then ask what does that do in terms of the types of things you could do in space. And then the last thing that we'll spend time talking about is just the fact that once you have this ability to put so much mass in orbit, it really opens the doors to everywhere else in the solar system. And there's a very famous quote that Heinlein is often cited as having said that once you're in orbit, Earth orbit, you're halfway to anywhere else in the solar system. And that's really a statement of the energetics of space travel. So getting from Earth to low Earth orbit out of the Earth gravity well requires a huge amount of energy. And in this plot, you can see it's about 9.3 kilometers per second. But once you're in low Earth orbit, moving to most of the other places in the solar system require less than that. So it's literally a true statement that you're more than halfway to most everywhere else in the solar system. So that's kind of our intro. And so with that, I'm going to start off, and I'm going to ask Ed a question here, get him to start pontificating a little bit on when we think about the existing trend and the number of things that are going into LEO. There's obviously a lot of stuff up there. There's huge opportunities that come from deploying these things. There's also some challenges. And now we think about something like Starship that not only could increase the numbers of things that we're putting in space, but also substantially increase the size of any one thing that we're putting in space. I'd love to hear your thoughts on what that kind of represents for the LEO economy, what we need to think about, the risks, et cetera.
I think it's really just a continuation of the trend that we're already seeing, as you pointed out. We're looking at something like a Moore's law in space going on right now. I think it's been going on a little longer than, the curve is actually faster than an exponential growth rate currently, because if you look at the doubling time over the last, call it 8 years, it's about 24 months. But if you look at in the last 4 years, it's like 18 months. So the growth rate is actually now currently faster than Moore's law, which is interesting. So I think the thing that people need to think about is if you think about everything Moore's law did for electronics, you need to think about the same thing happening in the space industry, starting in LEO and then eventually going out. So, some of the lessons of Moore's law are that when you deploy capital, you need to think about returns over 2 years' time, not 10 years' time, because otherwise you're left in the dust. If you, just think about how quickly things become obsolete. If anybody here has a cell phone that's 8 years old, it's a piece of junk, right? And that if the Moore's law is applying in space, then the same thing is going to be true of space hardware. So you need to think on those time scales. Obviously, there's ramifications for just the number of objects in space. So space traffic management, space security, it's a lot more complicated, and it's exponentially more complicated. So again, not linear growth here. If you build a system that can handle, tracking all the objects in space that is today, in 2 years' time, it can only do half of what's there. And in 4 years' time, it's completely obsolete. So you need to design your systems, especially for space traffic management, to be doubling every 2 years. Otherwise, you don't keep up with just the launch rate. So you again need to have this sort of different mindset. So I think, and then obviously science, there's a lot of issues that are going to be, a lot of both things you can do and things you have to be careful of not doing. So space is about to have that same mindset change that happened, and it's been going on in the electronics industry for decades.
Great. So Christine, space is now considered one of the very significantly contested theaters in the national security space. You've obviously spent your whole career thinking about these problems. Can you talk a little bit about not only what the current landscape looks like in terms of what we think about national security and its intersection with all the things going on in space, but also what things like Starship represent in terms of the long-term trends for that?
Sure, I'll give it a shot. Starship opens up, this picture is perfect, right? We just talked about LEO. LEO is so important for space resilience, but what Starship does is rapidly open up an affordable access to what's called cislunar space, which is depicted here, which goes to the moon and the region around the moon. And as this picture shows, there's some real advantages to being out there. So the U.S. is not the only nation that has recognized the potential importance of cislunar space. And actually, China is seeking rapidly now to have a first mover advantage. They've actually set a goal to establish a cislunar economic zone that favors China by 2050. And so it's a competition already, and it's just sort of being envisioned, right? And Starship is going to really enable the United States to play in that, which is pretty important because China is already doing things like, we don't know what they did, but they landed on the unlit side of the moon. They have successfully done what's called a Lagrange point, that L1 there in orbit. So they've had a soft landing already on the moon. So they're moving out, and there's resources, and they're important potentially economically on the moon and on the asteroids in the cislunar region. I think a little bit more of the dark side, which is sort of the national security perspective, sorry folks, but you could militarize this region. It's very easy to hide in cislunar space. It's big. We just talked about the challenges of doing space situational awareness in low Earth orbit. There's a lot of stuff to track. But think about trying to track things in that entire volume that's shown on this picture. So it's pretty easy to hide. If you hide in these particularly attractive regions that don't require a lot of delta V, a lot of gas, you can stay there a long time. And then you can appear and easily come down and enter one of the Earth orbits for various reasons that one can imagine that are kind of scary. So a challenge for the future and an opportunity for the United States is to think about how we're going to operate in this area. And that is just beginning to be thought of.
Great. So maybe playing on that a little bit, and I'll start with you again, Christine, and then we'll get Ed to chime in. So when we think about that kind of played out and imagine a future where we're operating in the cislunar space in a big way, we need infrastructure. There has to be more than just a big rocket, right? We have to have, we know already that, Starship is planning to do refueling. So now we have the ability to fuel things in orbit, and that changes the whole energetics of how you move around. You mentioned that we don't really know what's out there, and so there's, it goes back to the LEO Labs problem. How do we track? So can you all talk a little bit, maybe starting with Christine, on what else needs to happen besides just a big rocket to really start to bring this future?
Yeah, so infrastructure is really critical. And again, I think Starship, with its great capacity to carry large quantities of things into this region, is going to be really important. And so if we're going to actually be playing in an economic zone in this region, we're going to have moon bases, right? We're going to have infrastructure on the moon. China's next planned mission to the moon is at one of the poles, because that's where they think the water is, right? So water is a resource you're going to have access to. One of the big economic attractions of the moon is mining. There's normal elements there that will have some value, but there's also the potential for rare earth elements. And so you're going to have an infrastructure to support mining operations. So infrastructure is something that will have to be built up over time. Starship is an enabler for that, but it's just an enabler. There needs to be a plan, and there also needs to be kind of norms, if you will, for what does it mean to have a colony on the moon? How do we interact between Earth and Moon and other nations on the moon? What are the kind of rules of the road for what you can put in this space? So that all has to be sorted out.
Great. Ed, can you talk about the infrastructure, maybe also from the perspectives of traffic management? Like, what do we need to do to know what's out there and how things are moving around?
Yeah, you have the capacity when Starship comes online to launch a ridiculous amount of mass. Rather than 10 tons, you're talking 100 tons at a time. So that you can do one of two things. You could put up 1,000 small satellites instead of 100. Okay, that's interesting. And that is actually SpaceX's plan for Starship. That's why they built it for Starlink to do that. But you can also put very large pieces up at a time. And the key to infrastructure is often very massive things, especially if you're talking about fueling depots or infrastructure on the moon or that sort of stuff. And I think people really need to open up their minds. People have in their minds, because of years of everything they've learned about how space operations, you have to save every gram. You have to test things out. Flights are infrequent. You need to have a plan and a backup plan and a backup plan to that and a backup plan to that, because you only get a launch once every 10 years. That mindset needs to be thrown away, okay? You now have a flight on Tuesday. Which Tuesday? Every Tuesday, right? Do I need to have a 10-year development plan? No, you need to experiment and try things, because with the price coming down by a factor of 10, now you have the ability to experiment, and that allows you to get into this rapid iteration cycle. So I think, again, mindset change is going to happen here, and whoever grasps that first is going to win.
Yeah, great. So I'm going to play off that a little bit more. I think we had an interesting conversation at dinner last night, which was, this question I think is being debated in the government, but I think it's relevant beyond just government missions to commercial things too, of, historically we built big school buses and we launched one of them. The revolution of the last decade has been you can launch many small things and do things that are not necessarily the same, but can be complementary or can in some cases replace the missions. Not always though, and so there's I think there's an ongoing debate about which mission sets you can break up into many small satellites versus you still need the big exquisite school bus in space. And I think the interesting question here is, in some ways Starship starts to break that tension a little bit, in the sense that because of the amount of mass, because we believe the costs are going to continue to come down per kilogram, you can imagine, to Ed's point, launching a lot of bigger things. So that is starting to release some of that tension, but maybe not all of it. And I'd love you to talk a little bit about how you think that will develop as we get to this capability.
Yeah. So I can start there. I think for the Defense Department and the intelligence community, as you just said, Johnny, for years and years and years, we designed, built, and put up school buses in geo orbit a lot of times. And they're really expensive, really exquisite. All of the mindset that you talked about, Ed. You know, you do it, you've got to get everything right. You do it once, not every 10 years, but maybe 20 in the Defense Department, and then of course it lags for another 5 or 10. So it's a big thing, right? And
now you're talking a quarter century.
I know, but it's sad but true. And so they go up, and then they have this wonderful capability, but they're also big, fat, juicy targets. And as we have been able to see and talk more openly about the fact that this is now a contested environment around in Earth orbits, then those very exquisite things start to look a lot less attractive because there's not many of them and you don't need a lot of things to take them out. So proliferated LEO is really attractive because now you've got tons of targets. You can't take all of Starlink out. You need something else. But if we start to do the mindset that you referenced, where we put more big things out in further out space, then that could change the paradigm. And so that will change what we can do, the capabilities we can achieve, but it will also change the sort of contested space paradigm. And it, you know, because big things way out there are still gonna be hard to get. So maybe there'll be a window where we can have the benefit of the large capability, more of them for a while before they're too threatened, and kind of give us that advantage, or maybe not. And I think that has to unfold, but it's a really interesting question.
I mean, we're already seeing operations change radically in space. Mm-hmm. You know, at Leo Labs we track about 15,000 objects currently in low Earth orbit. And we see thousands of maneuvers per day happening up there. It used to be that maneuvers were a fairly unusual thing. You know, there would be only a few of them. Now we're seeing thousands per day happening. Primarily this is due to Starlink, which is continuously maneuvering. But it's not just, you know, to get to your point, that a lot of these are Chinese maneuvers. A lot of these are happening in rapid succession. And you can see that there's practicing going on for interesting operations happening. And we can see all this happening. And at the rate of change that we're seeing things right now, even in 2 years, it's going to be even a different situation. Let alone the numbers change it's going to happen, the doubling in numbers of things, but the pace of operations has changed.
Great. Okay, we're still sticking on Starship, but I'm gonna shift gears a little bit and think about some other implications. And Ed, I'm gonna start with you. So, you know, you were an astronaut. You know, a lot of the mentality of the systems that you flew were based on this older paradigm of everything has to be perfect, every gram counts. We lost the ability to really leave LEO after the 60s. So what does Starship represent for the future of manned spaceflight?
Oh, I think it's tremendously exciting. And I think what's going to happen too, is not just, we talk about Starship, there will be copycat Starships or Starship-like type things. It's just the natural progression. And the ability to put that much mass in a single go allows you to build infrastructure on say the moon, someday Mars. I think, again, if the lesson of Moore's law is that everybody overestimates how much progress there will be in the short term, and everybody underestimates how much progress there will be in the long term. Again, doubling every 2 years is 3,200% per decade, okay? So get that number in your mind, 3,200% per decade in just capability to throw stuff up there. Where are we going to be in 10 or 20 years? Don't bet against there being moon colonies or Mars colonies or things like that. These things could happen much sooner than you think. And I think that's going to be fantastic. It's no longer going to be the province solely of government astronauts. It will no longer be the province of solely American astronauts. There will be all kinds of operations. And I think this is just a natural progression. You know, this is the great age of exploration from the 1500s, but our modern day version of it.
Great. So Christine, you spent a lot of time obviously thinking about federal procurement. So, whether it's manned space flight or defense systems, what is some of these dynamics we're talking about? The ability to launch much larger things at lower cost, the timelines that Ed was referencing needing to tighten, and if you're building 10 years out, you're already behind. What does that imply for how the federal government needs to change the way that it procures things?
Yeah, so Ed already mentioned it requires a paradigm shift in our thinking, and I think that in the commercial world, just being with you, Jonny, I mean, you're able to change quickly. DoD, not so much. I mean, it's a big organization, and it's got a lot of responsibility, and that kind of rapid paradigm shift in your thinking is difficult for the Defense Department. I would argue it's difficult even for NASA to a degree. And so how we handle this paradigm shift, it's going to be commercial technology that's going to drive the Department of Defense, the intelligence community, certainly not the other way around. It's already happened with the proliferation of LEO, and they adapted a little slowly, but less than 10 years, and that's for DoD scale, not bad, but they're going to have to do a lot better. And that's going to be a real challenge. And if I could just add one other thing, when you look from a national security perspective over time, every technological advancement has led to a lot of unintended consequences. Many of them really good and positive, some of them not so positive, right? The classic example, internet. Whoever thought we'd need a cyber command just to defend things like our grid and our communications? Every time that happens, it's a failure of imagination. This really stretches your imagination. And so we're all going to have to be very imaginative as we think about the possibilities of what these capabilities are going to mean and how rapidly they're being introduced. It's going to really stretch the Defense Department, I can tell you.
I mean, isn't there already a precedent, Christine, and Jonny too? The federal government has had to deal with the electronics and computer industries, which do operate on these development timescales, these change timescales. So, they've had to deal with that. So why should space be any different? And they buy commercial, right? They in those areas because that's where the forefront is.
Yeah, that's true, and they are grappling with it. But the partnership, I will say, that's needed between DoD and commercial industry, whether it's electronics or space, is something that still needs to be pressed on and developed and reformed, because it's just not the way the department was built. Yeah. But it's working, it's evolving.
Mm-hmm. But so for instance, in the 60s, the electronics industry was a lot driven by the needs of the Apollo program. Right? Microelectronics developed very, very rapidly in the late 60s because of the needs of the Apollo program. And then eventually the needs of the commercial world grew so fast that it became larger, and then, and it transitioned. And I think we've seen the same thing in space, right? I mean, most of the development early on was government supported.
Absolutely.
But it is now, we're making that transition that we made in 1965 in electronics today in space.
Yeah, that's great. And I mean, I was wondering whether we'd be able to insert this little piece, but I think we will. So there's a very interesting book out there called Technological Revolutions in Financial Capital by Carlota Perez. And really the thesis is about there have been these major paradigm shifts in technology and economy over the last couple hundred years, starting with the Industrial Revolution. And that usually those are fueled not by a single technology, but by the confluence of a set of technologies, certain capital market features, and infrastructure, and all of those intersecting together. So, for instance, during what she calls the age of steam and railways, which is really when railroads took over, steam engines were obviously an enabling technology, as were things like rolling stock production. But there was also critically things like ports. Global ports started getting built. The postal service existed. Cities started getting centralized gas, which allowed for energy to be used in a very different way. And those things together, working with certain trends in capital flows, is really what caused this massive exponential change in terms of the ability of locomotives to move things around at low cost, at high volume, et cetera. And so as we think about Starship as an enabling technology, can we talk a little bit about what are some of the other enabling things that need to happen that are either technology-based or infrastructural, whether it's in-space refueling depots and ports, whether it's a network, a communications network in cislunar space. Maybe I'll get Christine to start, and then I'll move to Ed.
I would add on, we need to think about navigation. This is a three-body problem out here in cislunar space, so we're going to have to reformulate the way that we think about navigation, the way we think about tracking bodies. It's a completely different algorithm that you're going to need to do the space situational awareness out there. So there's some real advancements in sensors and algorithms and communications and geopositioning and that we're gonna have to have. And if I could add a category, I would add the category of policy, because I really think that this is an international world that we're coming to, and it's happening fast. And so we need to have international conversations about what are the norms of operating in this world, what are the things that we need internationally to invest in, to your point. And so that also needs to happen. And in this space, because commercial technology is driving it, I think it's a little bit of a difference in that commercial companies need to start thinking about how they play in the establishment of international norms. Usually that was all government, right? And government will, of course, need to be there, but I think it's the commercial technology that's going to have to drive that, and that's a different conversation than we've had in the past.
In the short term, I think the space traffic management and the space situational awareness is probably the first sort of blocking thing that we're going to run into in the very short term, and that's just because of the traffic jam that's happening in low Earth orbit. And that's where the policy and the government, the regulations and policy are going to play a role here in sooner than people think. But also the technology, because from a security standpoint, you can't think about an adversaries. I'm going to monitor all their satellites all the time. I put an analyst on each one. It doesn't work when they have 10,000 spacecraft, and they're all doing a maneuver every single day or multiple times a day, or just collisions in space, just the debris problem, and management of constellations. So I think the issue of scaling of space situational awareness is critical infrastructure. I would put it that way, and it's sooner than people think. Again. Even when we started Leo Labs, there were 800 active satellites. It's 10x since we started this company. And in 2 years, it's going to double again. In 2 years, it's going to double again. Okay, well, 400% in the next 4 years. All right. You've got to grow exponentially at a faster rate than that. And so all of our plans at Leo Labs are towards that. And I think tracking and situational awareness is you need to think of that as critical infrastructure also.
Great. Okay, so we have a few minutes left. Last topic. This hopefully I think is one of the more fun ones for this group. I know that all three of us in various forms are very interested in science as well, and like what we can learn about our world and the universe. We're at Muon Space. We're very focused on learning more about the Earth. Christine and I met on a panel that was really focused on how we can help scientists better get things in space that they want to make measurements with. And so I think the other thing that I'm personally very interested in, I expect y'all are, is this capability to launch the amount, the mass, at the cadence and everything else into space that Starship represents will mean for how we think about science in space, whether it's looking back at Earth or looking out to the cosmos. There's a proposal that's been floating around for a couple of years now for something called the Starship telescope, which is basically taking a 6-meter mirror that was originally developed for a ground-based telescope and just flying it on Starship as sort of a James Webb-like thing, but doing it quickly and inexpensively. And so whether that will work or not is an open question.
1/100th the cost.
1/100th the cost, right? And probably a tenth of the time. And so whether that specific concept will work, it does start to stimulate the imagination on what this capability will allow us to start thinking about doing when it comes to science. So Christine, maybe I'll start with you.
Well, I think it's incredibly exciting what we can learn from what Starship can enable. You can now launch, as you said, you can launch large sort of scientific labs and keep them in orbit pretty far out. Maybe keep them in orbit, around the moon or on the moon. You can look at how much we've just learned from James Webb. It's kind of unbelievable. And so I think that if we could launch telescopes like that and put them out there, then yes, absolutely, we can learn a lot more about that. I think the other thing that's really interesting is we can learn more about the origins of the Earth and the path that it might be on. Where we may or may not want to learn, but we should learn, and but also kind of what that might mean for other bodies in the solar system and beyond. And so I think the scientific opportunities that it opens up are huge. And frankly, in the past, it's also been a place where countries can come together and work together in a peaceful way that is also very good for establishing norms of behavior. So that's also very attractive.
That's great. And I mean, I love to think about, with as much as James Webb has shown us, what if we were launching a James Webb once a year? Or you're the successor to James Webb once a year, ideally not built on a 30-year time scale for $10 billion, but leveraging some of these unit economic changes to do things a little bit differently. So Ed, what are your thoughts here?
Oh, I have my wish list of things I want to see happen. So I'd love to see imaging of a extraterrestrial planet. You need very large optics, very large light gathering ability, and some very good coronagraphs to do that. But with active coronagraphs, that might be possible. Again, it's all about cost. We can do these things, cost and time. And you need to make these things doable on a graduate student's career, right? If a project takes 30 years, then the graduate students do not work on it because you'll never get your PhD doing this unless you're building one little widget. Okay, 4-year timescales. That's what we need, and I want to see that. I would love to see a wide field survey telescope, the equivalent of the Vera Rubin Observatory, which is coming online, the world's largest ground-based observatory for surveying the sky. First light later this year. For finding and tracking asteroids. Asteroids are super critical because they are where the resources are. They tell us about the formation of and evolution of the Earth, and most of these are part of a failed planet. And their distribution of their orbits tells us about how the solar system evolved. And finally, they hit the Earth. And so, knowing the locations of all these asteroids is essentially mapping the solar system. So again, I sort of hark back to the age of exploration where, why did Italy and Portugal and Spain and England spend all their treasure mapping the Earth? Because they knew, there was security, there was science, and there was trade. And for the same reasons, I think we need to map the solar system. And I think the key to that is a very wide field of view astronomical imager in space. That's possible now. 5 years ago, I would have said, Vera Rubin is the way to go. Best you're going to do right now, but I think that equation has changed.
Yeah, and there's even some proposals now for the next great telescope to be built in craters on the moon. Again, to build a giant telescope in a crater on the moon, you would need this capability. You would need to be able to launch huge amounts of mass and have the infrastructure.
When you don't have to do it like the ISS, piece by piece by piece over 20 years, then you can build and test, fly, iterate, and it just changes the way you develop projects like this. And I think we can bring the timescales in by a factor of 10.
Great. Okay, well, I think we're close to time, so I want to thank both of y'all so much for joining me up here today. It was a fantastic conversation, and thank y'all for having us.
Thank you.